πω εγώ. Ευχαριστώ για την πρόσκληση. There was a slight misunderstanding on the invitation. I thought this session was in Greek. But on the other hand, we have foreign participants. So my slides are in Greek. I will talk in English so that you will possibly understand what I'm saying. I will be presenting work done and the results of a project, FP7 project, approaching completion. It's called the SEMEOTICONS project. And the difference of this project is that it is not focusing on health, but rather on wellness. So in a sense, I will be talking about the design of a so-called an intelligent, multisensorial, unobtrusive, therefore Internet of Things. It's somewhere in the environment, it's a platform somewhere, sensing and understanding my state of affairs and wellness. Basically, the idea stems from years of experience from the Pythagorean ages. It is known, it is an established fact that the human face is a mirror. It conveys a lot of information with respect to our emotions, our health, and our status, well-being status as a whole. Darwin started and contributed to the study of human face and emotions in more recent studies, and basically the idea of the project was to explore the human face and the information that is conveyed in different types of circumstances, and to translate that measurable information into the semiotic code of the human face into measurable things so that we can focus on the cardiometabolic syndrome and disease in the context of wellness management. So basically, the idea of the project was to attempt to design a smart mirror, a mirror that would exist somewhere in our living room, in the gym, in a wellness and fitness center, and through which a number of biometrics and morphometric information, emotional analysis, spectral analysis so that we can detect information, a range of information, as I will be explaining in the subsequent slides, so that a risk model at the end of the day is developed and communicated, and the system, being intelligent enough, would provide advice to the individual with respect to its management of wellness rather than health. Going to the literature, one sees that there are a range of risk factors that can be classified in three different basically dimensions: physical, emotional, and lifestyle, that constitute risk factors of cardiometabolic diseases. So from measuring things such as stress, fatigue, and anxiety, or glucose and metabolic characteristics, heart rate, dietary habits, and physical exercise, etc., etc. So there are a range of risk factors, and our objective was to unobtrusively attempt through a device that exists in our surrounding, the smart mirror, to measure, estimate, and reach conclusions with respect to the state of an individual. So classically, from the classical computer science, there are a lot of challenging computational things that need to take place, but I would move without focusing on trying to explain this in basically describing the process that had to take place. Video, the mirror sees the environment, is equipped with cameras, and therefore it's able to monitor the environment, and then a number of computational activities need to take place, from face detection to, for example, any reconstruction, to estimation, morphometric or calorimetric or other multispectral imaging methods, so that at the end of the day, a multidimensional, we call it virtual individual model, is developed, which is then the basis for decision making, for guidance, for coaching, which is the objective of the mirror. I will be very briefly describing some of these findings and where we currently today. Now, the first serious problem is, we said, the mirror needs to identify, to understand what they see. So the problem of face recognition and identification is a key problem, and I here present some indicative problems. We know that the state-of-the-art algorithms today, they can identify faces, but they can identify faces that are not really human faces. And therefore, we had to address these issues, and we had also to address issues such as erroneous estimation when the face is occluded, or when there is excessive motion of the head. So in a sense, there was a significant beyond state-of-the-art activity in developing methods that would enable us with 100% accuracy to track and estimate the face on a video sequence, which is a series of temporal images, so that we can then move into the computational aspects. And as I said, I will be talking about some of the computational approaches. As I said, stress and anxiety is a risk factor for cardiometabolic diseases. So we need automated methods to estimate stress. The literature shows plenty of such evidence, and the question is, well, how is stress measurable from facial expressions and facial features? Again, going to the literature, we see that there are a number of quantitative aspects: blink rate, eyelid response, eye aperture, skin color, heart rate, mouth shape, lip deformation, gaze direction, etc., which relate to the presence or the scale of stress and anxiety. So we engaged in computational approaches to estimate rather than, and of course there are different approaches. We can use ECG device, galvanic skill response, but we want non-intrusive. Therefore, we're working with the video, and we selected appropriate methods for the estimation of such quantitative descriptors extracted from the face that would enable us to estimate the presence or absence of stress and anxiety. Motion from video through appropriate algorithmic processes in three-dimensional spaces, we reach a situation where we measure specific features and quantify features that relate and monitor the movement of the head, which I said, based on literature, relates to the presence of stress and anxiety. The behavior of the eye, the blink rate, the circumference of the eyes, the size, the direction of the gaze, all those are important, as I said, features. And again, through advanced computational methods, such features were extracted. Mouth. Mouth and the characteristic of the mouth, again, relates computational methods working in the YIQ color space and advanced mathematical processing enable us again to extract specific measures based on the optical flow in imaging that quantified characteristic of the mouth. Heart rate estimation. Heart rate relates to explicitly to cardiometabolic disease. It relates and is influenced by stress and anxiety, as already said. So the question was, well, how can we optically estimate the heart rate? And there are two fundamental ways to approach this problem. The one method published and developed by MIT some time ago in 2002, it's called the Eulerian video of magnification. Basically what it tells us is, do I have a pointer? Is there a pointer? Basically what this method tells us, it's not working, is that if we magnify a specific video, I want a pointer to simply indicate the pointer on the screw. The Eulerian method of magnification, media unavailable. Anyway, it was playing in my... is one of the methods that allows us to see very subtle changes in motion as a result of the functioning of the heart system. There you see it. It's the same image applied in the other method, I will stop because I will waste all my time in trying to demonstrate the Eulerian method of magnification, which is a very interesting computational development. The other approach that we adopted, it's based on the so-called photoplethysmography. In a sense, we are trying to detect very subtle changes in color of the skin as a result of the heart rate. As the heart pumps blood, there are some very, very slight changes in the color of the skin, and through advanced computational methods, independent component analysis, and very methods that are beyond the scope of my today's presentation, we reach a state in actually estimating, by looking at the image of an individual, the heart rate. The question, is it accurate? Elaborate testing indicates that the accuracy approaches 99% as compared to the ground truth, which is ECG monitoring based on an ECG card, which for wellness management seems to be more than adequate rather than clinical decision making. So in a sense, at the end of the day, a whole process of extraction of characteristics, emotions, and a multidimensional space of measurable descriptors are calculated, which are then, through the use of computation and machine learning approaches, are classified in detecting a level of stress in an individual. Other characteristics that were also extracted and measured was the concentration of lipids under caloric concentration, and you see some indicative information of how specific and qualitative information is extracted by simply processing the visual information of the face of a given individual. At the end of the day, all these different, as I said, morphometric, emotional, calorimetric, and other descriptors that were calculated need to be transformed into what I referred earlier on to a model, to a risk model. We call it a virtual individual model. We defined it as a three-dimensional space with the axis being emotional state, lifestyle habits, and physical status. And there was a process of transforming these quantitative descriptors into a point into this risk model. And it's something like this that was the end result of the project. So basically, I explained the idea, some of the computational processes that take place in extracting and quantifying information, and these are our first prototype of the WISE mirror, the smart mirror. Depth sensors, multispectral cameras, and a high-speed 9 FPS video camera as part of the mirror that monitors the environment, calculates, estimates, and provides response. Version 2 of the WISE mirror, more advanced in terms of human-computer interaction, coaching activities, etc., that is able to provide to the individual in front of him. And we are currently in the process in which this so-called WISE mirror, unobtrusive monitoring in the context of wellness management is undergoing clinical evaluation in 3 clinical centers, Pisa, Milano, and Lyon, through an interventional open study in which 60 individuals, 20 in each of the centers, 10 men and 10 women are participating. The age range ranges from 25 to 60, and it is those who are interested in finding out what is the risk profile for developing cardiometabolic diseases, and if so, if the risk is high, to be coached, to be advised, to be guided on how to reduce that risk through behavioral change. So it is a device that senses, understands, and advises in the context of a specific environment. We don't yet know, because the evaluation study will be completed in 3 days at the end of October, so we do not know the results of the evaluation studies. Our initial feeling, it's taken very well, so we're rather happy both on the scientific work done in the context of the project, but also optimistic on the potential for future exploitation and capitalization of the system as developed. A very large group and individuals from Italy, France, Spain, Greece, Ireland, Norway and Sweden are participating in the project. Thank you very much, and hopefully I stayed within the time limit or slightly slightly below.